Okay, thank you everybody for joining. My name is Reza Nejabati. I am leading quantum research activity within Cisco as a part of larger research and strategy group within Cisco. What I am going to tell you today about what is the Cisco view, vision, and roadmap about building a quantum network. I know that last night you attended Killers, most of you, most probably, and today is the last session, so I said, let me do something else. So I do a killing technology. I cannot sing, but at least I can show you some killer technology that Cisco is developing. Hopefully, a little bit wouldn't be that boring for you, so it would be one of the interesting talks toward the end of the conference. So with that, let's go see what is the content of my presentation. Before we start, that's a standard Cisco presentation, WebEx channel. If you need to discuss with me anything, generally keep in touch with me via email, which is at the end of the presentation, or WebEx chat after my discussion. So what I am going to do today is a little bit give a tutorial for you to understand what is the quantum and what is the difference between quantum and classical. And if you go to the quantum realm, it's very big, very wide. I mean, from physics to math to engineering. What I am going to pick up, what are the properties of the quantum mechanics are important for us as a network engineer, and how we can harness to do things that is impossible to do with a classical or a normal network, digital network. So that would be the first part of my presentation. Then I go that, okay, with these possibilities, what really Cisco wants to do, what is the flagship goal in Cisco research that we have to develop quantum network technology, and also what we have done so far. I a little bit dig to that. And then I also discuss some use cases and market opportunity for quantum network for now and the future. And then finally, I have a demo. So 3 demos, in fact, given how much time I left. First demo is a recorded demo, so at least I don't embarrass myself if the network doesn't work or the real demo doesn't work. The other 2 demos are the real life demo connecting me remotely to our lab in Santa Monica. So I left that for the last 2. Hopefully works. I did another demo similar yesterday in show floor, works. Finger crossed today works. And then I try to give you ample time at the end, so if you have a question, you can ask me. So one of the technology also we announced a few weeks ago, I brought with me here. He's in the desk. You can come at the end of the show and have a look and have a chat with me. Okay, let's start. Harnessing power of quantum. What happened? Okay, so most of you, or all of you, are familiar with the concept of the bit. I call it, for context of this presentation, classical. So I want to separate it from the quantum. So I call it classical bit. Nevertheless, it's a digital bit. It's either or 1 and 0. But when you go to the quantum realm, it's different. It's a superposition of the 1 and 0. So always when you create a quantum bit, which from now on I refer to that as a qubit, which is quantum bit, is the superposition of 1 and 0 with the probability of the alpha to be at 1 and probability of beta to be at 0 at the same time. And then obviously the sum of the post probabilities are 1. Now, obviously if you want to create a perfect qubit, that has to be 50-50, but normally we don't manage to create a perfect qubit. Now let's see how we create this. So really, if you want to create this, you have to go to atomic regime to enter the quantum realm. So people work with a spin-off electron to create these quantum bits. One of the things that I like particularly, or network people like, polarization of the photons. Generally, photon is very good for networking people because we can put it in a fiber. So polarization of the photon, if I can create magically, which I show you later how this magic works, a photon that it has a polarization either diagonal or anti-diagonal, or vertical and horizontal at the same time, then I have created the qubits. So that's you see that a list of the technologies that you can provide for qubits, from nuclear spin, electron state, and so on and so forth. Now, really how to really, from material point of view, you build it. You can build it using superconducting materials, like a coil you see on the top. It really like that. In fact, IBM quantum computers work like that. And then you can play with the atomic structure. For example, you can charge atom to make the ion and rearrange them and create those properties of the superposition. Or you can basically create a defect in a, let's say, nitrogen, and then put another atom there and create these possibilities. Now, I mentioned IBM because most probably you have heard about the building quantum computers. Now, these are the, if you like, cartoonic graph of the quantum computing you can go, although not very mature one, but you can go and buy from market or rent from market. Being superconducting, Google and IBM, charge atom, which is few companies do that. You see they put an atom in the middle of that chamber, and then neutral atoms, like a rubidium, for example, is another one with the laser tweezer pointing on that, so to create those conditions. Now, let's forget about the physics of it. I want to show you, we are working at the atomic level, but let's see what is the big problem they have. You have seen the IBM big chandelier goes to a very wide chamber if you have seen the videos, but all of them, they have this problem. All of them, they have this problem. They have to make them stable enough. You can control the quantum interaction. You have to bring them at the near zero, absolute zero. So what they do, they put them in a chamber, vacuum it, and they inject the helium or nitrogen into that, and basically create a millikelvin regime. IBM machine works at 400 millikelvin, for example, which is near minus 300 Celsius, if you think about it. So that's a big problem. That's why you see how big they are. And even they are very, at the moment, our capacity are very small, but that's a big problem. In fact, in Chicago, they are building a slightly bigger than, still a small quantum computer, but they are deploying a small reactor beside it to be able to feed these cooling systems. So I want to give you a reality of what is really quantum computer and where we are. All this progressing very fast. Now, these things are very good, but the problem is that this material are really nice if you work them at a small scale, put them, cool them down, and vacuum them. But no way I can put them in these atoms in a fiber. It just doesn't go. The atomic scale movement is a very small macroscopic level. So these things are not good for transmission. It's good for for processing, localized processing. So what we need to do, as I mentioned, we work with the photon. So photon also, we can create a qubit. If we can create a qubits that are in the telecom wavelength or visible light wavelength, at least we can, using free space or fiber, move them around. So that's where is important for us. And the photon is good that you don't need really cool them down to behave in a quantum regime. Now, I go back at the technology, what we do with the photons for quantum and what is relevant to the rest of it. Well, let's a little bit, now I dig into the technology, see really why people bother to do these things. So one of the things with the quantum you can do, you can get a quantum computing supremacy. You have heard most probably about it. So if you look at the digital bits, or classical digital bits, a 0 and 1, 2 bits, it has 4 possible states you can create with 2 bits. But at one point of a time, you can use only 1 state of the 4. But if you have 2 qubits, because there is a superposition, all 4 possible states are usable at the same time. So that's the power of it. So imagine you create a 1 million qubits, how many concurrent possibility you have, you can use it. So that brings the power of quantum computing. So essentially, with the quantum computer, you see in the graph on, on the bottom of the screen, for a very big problems, I go to the type of problem that they can solve later, but for a big problem, like breaking a code, cryptographic code, for a normal big supercomputer, may take a decade or even more than a decade. Essentially, the time exponentially increases when the problem becomes complex. For quantum computer, linearly increase. So you can do it in a matter of days or weeks, yeah? Now, quantum computers are not universal computers. They are very good to solve some problems or create some problems, if you like. On solving a problem, for example, anything to do with you want to model molecular interaction, which drug design is one of them. New materials is another one. Weather forecasting, some forecasting or prediction. Optimization, they are very good for it. And modeling. The other thing is the cryptography. Cryptography, not they can do cryptography, good cryptography, they can break very well cryptography. So because of the power that they have. And that's where all the noise comes that we have to be quantum safe and so on and so forth. Because the quantum computer become available, then they can break because of the power that they have, cryptography. But having that bad side aside, they have many good applications that you see example of them in there. Now that's a quantum computer. With the quantum bits, you can do more than computing. You will be surprised that the most mature quantum technology in the market, in fact, you can go and buy, is the quantum sensors. So quantum sensors, again, you create a qubits in material, they are very sensitive to environmental change. You can make the type of the quantum sensor that are sensitive to RF, sensitive to temperature, electromagnetic field, you name it. So they are very, very good sensors. And they often can go up to 10,000 times more accurate than a sensor, equivalent of a sensor in classical domain. So at the moment, you can buy quantum sensing for sensor for timing. Military actively use it for the location and position verification. You can do the RF sensing. In fact, there is a demo of it we have done, which is you can sense the RF spectrum from 1 hertz to multiple of terahertz with resolution of 1 hertz with one sensor. That's a crazy. I mean, for the people that work on RF domain, it's crazy. So I want to show you the power of that. Modern MRI machine, they use quantum sensors. So that's also show you that the quantum is not really science fiction. On the computing side, it's getting there. On networking side, we are building, I explained to you, but sensing is pretty mature. Now, another thing you have heard a lot about quantum security. You can use the quantum bits to transmit secure information. For example, your key for cryptography. The reason is that because quantum mechanics follow a very important principle, no cloning. You cannot, if you read a quantum information, quantum bits, you cannot clone it. Essentially, a quantum bit is in the superposition state until you have not measured it. Once you measure it, it collapses. It comes to the classical domain. So therefore, nobody can clone it. So that's very good. If you send, for example, imagine you send your key from point A to B or Alice to Bob here using quantum key distribution, using quantum bits. If eavesdropper in the mean, adversary attacker in the middle, try to copy, it can copy, but it cannot repeat and send it to the Bob, so Bob doesn't use the one that doesn't receive. So that's a pretty robust mechanism for distributing information. Yeah. Now, let's go to a spooky version effect of the quantum. Now, entanglement. So entanglement means that I can create two quantum bits, if you like, are in superposition, and make them entangle together means that they are completely coherent with each other. Doesn't matter how far they are from each other. Without any connection, if I do something to one, the other immediately reflect that change. We call it entanglement. So that's where Einstein called it a spooky action. So, and in fact, that's possible. We do it in the lab. That's the device that you have in front of me, is doing that quite efficiently, actually. Yeah, we can do in Cisco. I go to the 100 kilometers of entangled photon different, so they can really be entangled together by 100 kilometer distance. So that's the entanglement. Now, what you can do, okay, I have a two entangled photon. They are completely coherent. Whatever I do with one, the other one reflects. So what you can do with that, you can do a Star Trek stuff with it. You can teleport, not human, but information. You can teleport information. It's very much possible. It's really not a science fiction, it's possible. So what you do, let's say I created two photons. That's a microscopic picture of two photons. They are entangled. I put them in distance, that's called B and C. I put it in distance, and they are entangled. There is no physical connection between them, just they are entangled. I put them in distance. Okay, now I want to teleport information from position of B to C. What I do, I create my information, which is A, and mix them with B. The mixing, I really simplified it. It's a complex process, but we mix them with it. Imagine, let's ignore that part. We mix A and B together. That mixture is teleported immediately to C. Because I have changed the state of the B, and that change is reflected. So that's mixture. So that's also, we can do it in Cisco now. Not as a product, though. So we can do it, okay? So that's now you have your imagination go wild, what you can do with this stuff. I mean, there are all sorts of use cases that there is no equivalent in the classical domain with it. I go through a few of them for you today, and we discuss them. Now, there is an important here. So when this experiment was theoretically and also in a smaller scale done with a scientist called Rosenberg, Einstein got mad because Einstein said nothing can go faster than the speed of the light. But that's instant. So what they did, they worked together and they have solved the problem. It goes faster than the speed of the light, but the problem is reconstruction. If I want to, the whole point was that I basically teleport A, which was my original information, to C. Okay, that was the whole point. But the teleported one is a mixture of A, B, and C at the receiver. So this mix, you need to separate them, extract A. To extract the A, you need to know at point of the C, at the time of the teleportation, what was the state of A and what was the state of the B when they combine together. That information has to somehow come to C, and that's not possible you need to just use the normal internet or normal network to send that information, so C can recover that. So the mixture is go instantly teleported, mixture of A and B to C, but for C to decompose A and B from each other, need to know what was the state of A and B at the time of the teleportation. So that part, basically they call Einstein-Rosenberg paradox, means that although you can teleport faster than the speed of the light, but you cannot reconstruct faster than the speed of the light. So that's what still is very, very, very useful, and you can see that this effect has a practical application in finance sector today. Now, I explained to you, let's move to the networking. I explained to you that about entanglement, teleportation, everything. Let's see what is the quantum version of networking and what is the difference between classical networking. Let's look at the classical network. I created data center architecture. It's easier to explain it. There's just no purpose particular. That's a classical version of it. So if you send a bit from Alice to Bob, it just go hop by hop. Depends on if you are layer 3, layer 2, you do the switching, you do the routing, whatever you do, store forward. That's how the digital information goes. Hop by hop, you go from Alice to Bob. Now let's see the quantum version, and then you send the next information after each other, and you try to increase your rate as much as you can. Now let's see the quantum version. The quantum version looks like this. So I changed the color of the switches because the classical switches doesn't work in this case. We go through that later on. And then there is something extra that there is an entanglement source. So something that generates entanglement. So there is an entanglement source somewhere in a network. I put it randomly there for illustration purposes. So that source generates pair of entangled qubits. So like this. Let's say Alice and Bob want to communicate. They use, each of them use these entangled bits or photons. That's like a box. So they don't have any information. They are just quantum bits, which are entangled together. Now, Alice wants to send the information to Bob, puts his information, let's say, to this box, which means immediately teleported to the other side. So that's how a quantum network works. So you see, I don't send quantum information. I send the carrier of the quantum information, which is entangled photon, and then I use that to teleport information. I hope I managed to explain it. So there is no store and forward and routing of the quantum information like classical domain. I just send this carrier, which are boxes, entangled boxes. These are carrier information to Alice and Bob. They use that to teleport their information. Okay. Now, let's see what is the state of the art in quantum technology. Existing quantum network across the world, when I say state of the art, forget about the university, where the operator, service provider, or enterprise is using them. For network, they use point-to-point, and mainly for key distribution. You remember I explained how it is good for QKD or key distribution because of no cloning. So they use it point-to-point. There is no network, one point to other point, and they use it for key distribution. Okay? And the biggest one by far in the world is China National Quantum Network, which is purely used for security and QKD. It has both satellite and fiber. The good thing is that with the photon, also you can do a free space to satellite. So they do that, not only fiber. So that's China. And then afterward, the serious one, there are a few others as well, but more or less they are the same size, like in Spain, London QKD network, that they provide for financial center, basically a service mainly for key distribution, for quantum key distribution. More than that, there is nothing, and all of them are point-to-point. So what is the problem with that? You cannot call them network, just a piece of fiber from one point to the other point. They are very specific to security use case. There is nothing else you can do with them. And for QKD, they need a very dedicated hardware, dedicated fiber, and or you need to carve out a big chunk of your bandwidth on existing fiber and then use it for quantum transmission. They are very costly. They are not scalable. Simply because they are point-to-point, they are not scalable. Okay, now introduction aside, let's move on to see what really in Cisco we are doing. So in Cisco, we are building a quantum network. Why? The reason is that there is a good momentum on developing quantum computers. There is a good maturity of a technology on quantum sensing. Now we are at the stage that really we need to create an infrastructure that network all of this together for both scalability and accessibility. So there where we are coming to, in the picture. So we are creating a quantum network. We call it Cisco Quantum Network. First of all, it's a scalable, multi-user, multi-tenant. It can connect quantum computers together or quantum sensors together, or these two technologies with each other. And for that, with that, we can build a data center, and we can build a, if you like, IoT version of the quantum sensors, distributed quantum sensing. Yeah, so that's our idea where we are going. Now, if you build that, since you are working with quantum information, security is inherent. Nobody can copy your information anyway, so it's completely secure, this network. You can use that network because the network, I show you, is not a point-to-point, it's a proper network with a topology switching and dynamicity. You can use to create a very efficient key distribution if you want. Anyway, our flagship goal is to build a network that connects quantum computer, build a quantum data center. I want to go through that, why that's so important. I mean, if we do that, the rest of them come as a byproduct. But this is the most important application, and most impactful one, that's why this is our flagship goal. So you remember this graph. I said that why quantum computer is good, because in the linearly, they can, in a limited time, they can solve very complex problem, which for a classical quantum computer would take an exponentially large amount of time. Some of the problem quantum computer can solve for a classical computer, it takes up to 100 years to do that. My favorite one, I list application that a quantum computer can by far surpass classical computer there, but my favorite one and most impactful one, I think the one that would be the first to use quantum computer is drug discovery. So at the moment, the science of drug discovery is done. But if you want to personalize for individual person a drug for individual disease of a person, then usually it takes beyond the lifetime of that person to design a drug. Because most of them try error, or you need a simulation, takes a lot of time. With a quantum computer, you can really do that fast in a matter of the weeks or months. Okay? So, and then new material. This is another fantastic application and very impactful one. I mean, with the quantum computer, really we're going to see a step change on design of, for example, battery for EV vehicle or EV airplanes. The most of the limitation now is that there is no way to efficiently model the interaction between the rare earth material to design molecules to design an efficient battery. So that battery, so that's the impactful one. You can see the rest of application there, we went through that. Now, the big catchphrase is that for that, you need a very big quantum computer, 1 million qubits. The reason is that because quantum, we went through that. The quantum are atomic scale, quantum bits. They are very sensitive to noise, environment, so you need to do error correction. To do that, you need a really large number of the set of qubits, and that's 1 million plus. I mean, for drug discovery, you need to think about 10 million plus. So that's, to give you a state of the art, Google research, IBM recent announcement was 174 qubits. So 174 today to 10 million that we need to do really something useful. You can see the difference. So that's why Cisco can play a role. The quantum computing vendor, they're perfecting the chip, they increase and increase. But 10 million or 1 million capacity is impossible monolithically. We know from the lesson learned from the data center, you cannot build, I mean, it really doesn't make sense building a large supercomputer. You want to build a data center using a smaller one. So that's why we are we're taking the same approach, hyperscale approach. We want to scale out quantum computers and create a network that a smaller quantum computer, larger number of them, are connected together, and we build a useful quantum computer. Yeah, so that's our focus. So if you look at it, we are focusing on distributed quantum computing and quantum networking for that. If we do that, we hope we really accelerate availability of the useful quantum computer that can do serious application like drug discovery. We bring it forward with 5 to 10 years. So let's look at the use cases. I promise you use cases. You may tell me that, okay, what are the use cases exactly? I mean, beyond the quantum computing. So I said that what we call use cases, quantum for quantum world. So connecting quantum computers, quantum data center is one of them. And quantum sensors, we discussed about that. Distributed sensing is another one. However, all of them, the quantum computing one especially depends on somebody builds a robust enough quantum computer I can put it in a data center, so you can use the Cisco network to build that. So that's, I am sure it'll come, but let's see what else we can do. There are a whole portfolio of other applications today can use our quantum network. That's what we call it quantum for classical. The one is the decision coordination. You remember I explained the concept of entanglement. You have two entangled qubits or photons. Whatever you do with the other reflect that. So imagine that you are in a fintech business, you are in high frequency trading, and you have two trading data center or trading station separate from each other. In a high frequency trading, you need to coordinate your decision very, very fast. Even the speed of the light between the two centers in the same city is too slow for them. If they have entangled photons, so when one center make a decision, the other one instantly get a copy of that decision and they can coordinate to sell or buy a certain stock at the same time. So that's really application that we see a lot from financial sector requirement that come to Cisco. They can use our entanglement network. The other is that secure position verification. Also that is coming from financial sector. So, and also defense. There are many applications in these two sectors that they would like to know a person is really is who he claim or she claim he is, and also they are in the same place that they claim they are. So it's important, identity and location. Location at the moment use GPS, but with GPS it's very easy to spoof it. But with the quantum entanglement network, there is no time for me to do detail of it. It's very easy to do the secure position verification very accurately and very securely beyond the GPS accuracy. Then time synchronization, especially in autonomous manufacturing and robotic industry, they would like to synchronize at the picosecond level two different locations for coordinated actions. So that's, again, entanglement network. Because of that instant transport of the decision can help you to basically coordinate or synchronize your clock. Another one is if-drop proof security. I told about the quantum key distribution to you, but imagine you just have your fiber carries your classical traffic, your internet traffic, and then you launch an entangled photon in it. So if somebody try to tap your fiber, the entangled photon disappear and they cannot clone it. So that can tell you that if you don't receive it, that somebody is tapping the fiber. At least there is a possibility that somebody is tapping your fiber. So that's another application. Now, if you look at it with our quantum network, we are building a network that connects quantum computer for a data center. or connect the sensor for distributed sensing in one side. That's our more future. We hope that in 5 years' time, that really technology from company to be there, that we can connect them. And then if you look at now, what we can do is on the right-hand side, those are the applications today we can deliver with our quantum network, and the classical network cannot do that. And this is a roadmap. I want to always compare our roadmap with the quantum computing vendors. So in the top, I got a public roadmap from major quantum computing vendor that they have it publicly available. For example, let's say pick up IBM. So they say on the top arrow, you see that today they are working at the quantum chip, which is 100 to 200 qubits. That's where we stand today. And then if you look at what we do today, I show you in the rest of the slide that we are building a network stack, which is the hardware and software. By 2030, major vendors in quantum computing, they said that they're gonna go to few thousand qubits. We will have our network fully scalable, software and hardware available and ready. After 2030, all of the vendors' roadmaps say that going beyond that to achieve millions of the qubit, they need to network it together. And our network will be ready there to build a data center and create a really useful quantum computer. So that's where our roadmap is that. Meanwhile, between 2025 to 2030, where the quantum computers are really mature enough, we have this application that I explained earlier that really can solve the problem of some of the customers now. I want to bring this, I don't know how you believe McKinsey as an analyst or a predictor. That's the market size analyst that is not Cisco, is McKinsey. I copy from them, that they say that what is the quantum computing market, conservative and basically, or optimistic, 2035 and 2040, and what is quantum networking and quantum sensing. And you see that the quantum networking has a sizable chunk of the market for that. So there is a value to be there. Okay. Let's dig into the technology a little bit. I told you that we want to build a quantum network that connects quantum computers. I also explained to you that there are multiple technology possible for quantum computer, from microwave to atoms. I told you, I explained all of that. So it's very difficult to see who is going to be winner. I think too early. So we are building a network that can connect any breed of quantum computer. So we are agnostic. If a couple of them win, good enough, we can connect them. If one of them win, we are ready for that. So who is going to be better performing? Maybe it will be a combination of them, depend on the situation and application. We can connect. So our network is agnostic to quantum computing technology. That's one thing. Is the scalable, very high performance entanglement distribution network, is a multi-user, multi-tenant, and we have divided our technology development stack in two parts. One is the hardware, we call it quantum network fabric, Cisco's quantum network fabric. One is the hardware stack on top of it, does the control, protocol, and orchestration, we call it quantum network orchestra. So these are the technology we are focusing at the moment. On the bottom is the hardware side, fabric, quantum network fabric. We are building entanglement source, which is here, you can come and see it. Or we built it already. We are developing a quantum network interface card, where the network connects to quantum computers. We are building quantum measurements. We are building quantum switch. We are building quantum memory. And also on the software side, Cisco always pioneered protocols in internet. We are pioneering here as a protocol on entanglement, distribution, and routing. We have several patents and publications on there. And then we are building a compiler that can allow us to do distributed quantum computing. So I am going to very quickly go through these four technologies. Just to remind you, for a quantum network, we need an entanglement source. What does an entanglement source do? That's a reminder, I explained this. create two entangled particles. We call it box. They are photons. That boxes are used by source and destination to teleport information. Yes? Just to remember this, that's important. Now, that is our quantum entanglement source. I mean, that's amazing performance. We are by far world leading and world record breaker on this. This chip you can see here, basically we pump a laser in it. For every single photon goes in, it generates two entangled photons. And it generates at 200 million pair per second. Very efficient, 99% fidelity. Very, very low power, 1 milliwatt. Obviously, it's a small photonic integrated chip. You can put it there. That was a sign of approval. So that's now. Let's look at this one. I mean, I don't go to that, but I want to show you some result. It's not really a box here. It's working. That shows what we do. We have a ring sort of a structure inside our chip. When the photon goes, we interact with the ring and material that builds the ring, and every photon is converted to do different entangled photon. This shows a spectrum of the output of the chip, and then you pick up the red one is the laser that we pump. The two yellow one are two entangled photons at two different frequencies, and they are coming out. So I want to just show you how does it look like if you try to look at it in a spectrum analyzer. It's real. Next thing is the quantum NIC. That's a bloody difficult technology to develop, and we are cracking it. I tell you why. Is because you see, on one hand, you have on top your quantum network technology, quantum computing technology. They are working in this regime of superconducting, charged atoms, and neutral atoms. Let me give you an example of what are these examples. A superconducting regime is microwave frequency. The charged atom is around 300 nanometers frequency. Neutral atoms, 400, 600 nanometers frequency. So it depends. So that's the frequency. What we are working on, entanglement chip, what works, because we can put it in a fiber, is a telecom frequency, 1500 nanometers. So on one hand, I have a carrier on my boxes that are 1500 nanometers because I want to put them in a fiber, move them around. On the other hand, I have a quantum computer I need to connect, which is completely the other side of a spectrum. So that's why I need a network interface card that convert these frequencies together. So that's where we are building. So that's really a mismatch here. So our network interface card, what we do, we try to create a photon close enough to frequency of the quantum computers. We shoot them to quantum computer, and that excites them through some interaction to create a photons that are mapping the internal qubit to a photonic qubit for us to use. I give you a little bit better explanation here. So what we assume that a quantum computer has to allocate certain number of the qubit for communication. So we try to use them to excite them to convert their wavelength from the computing wavelength to optical wavelength. So how we do that, that's an example of one of the things we do. So this particular one, we use the rubidium atom confined, rubidium gas as a cloud of atoms, confined is a glass vase. It's really glass vase, you can see it, I mean that big. And then what we do, if we again shoot with the laser, then what does it give us? Two photons, one in the near IR, which is around 700, the other in around telecom. We put which are entangled together. We put the near IR to quantum computers, can interact with quantum computer more closer they are to their frequency, and we use the telecom to put in a fiber. Whatever quantum computer does to near IR, which can work very well, some of the quantum computer with that, is going to be translated to a telecom frequency. That's not a chip, that's a bigger size, a 2 euro rack size network interface card. Now, this is another beauty we are doing. So switch. Now you want to generate this entangled photon. You remember my figure had a switch which are pink. I said they are different. That switch has to not only switch the entangled photon, but has to keep the quantum properties. If you use the Cisco off-the-shelf optical switches, or anybody, Nokia, Huawei, whoever you want to use, they're gonna completely mess up your quantum mechanics feature of your photons. Whatever you get is not anymore entangled out of the switch. So we are building our own switch, which is essentially a photonic integrated chip, and not only allows us to do the switching of the entangled photons, but also allows us to share a lot of our resources. I go a little bit into that. So for the first time, I am showing outside what is the architecture of our switch. This switch is being fabricated at the moment out of fab, and we are about to test it. So the switch basically gets the entangled photon, convert them to what we have developed and patented. We call it path entanglement. So it means that the information exists on the top part and bottom part at the same time. That's quite a strange concept, but that works, and then it allows us to switch without doing any damaging quantum properties of the photons. So, well, by the way, on a bracket, whatever I explain here is not a product. It's an R&D prototype. So it's far, far, far from product. Just I want to make sure that everybody understands that. So this switch, stay tuned, we're gonna have an announcement about its performance and features very soon. But what we do with this switch, we connect all these things you see on the top, our source, our measurement devices, and then quantum computers with it. So it allows us to move these entangled boxes around between different processors and allow them to communicate with each other very flexibly. You can use it for anything else, flexible networking. Now, we are building a data center with that data center network or fabric with that. I put the picture like this, but it's not exactly like that to simplify. So our network, we are not building we are not doing academic practice there. On building this network, we think what are the techno-economy consideration for that in terms of the cost of operation, OPEX and CAPEX of this. So we are building a network for the short distance, has a network type 1, which works at the near infrared. That allows us to create a more cost-efficient equipment for measurement and detection. At the longer distance between the racks, it works at the telecom regime, which is okay, I am approaching final part of my presentation is software side and protocol stack. The only thing I want to tell you that what we are building, the whole stack of the compiler and network control for our technology. So on the very top corner on the slide, let me get to see if this works. Yes. If you see the laser pointer, which I don't see myself, yeah, the laser pointer here, this is the typical people that works on the quantum algorithm development. The quantum algorithm comes like that. If you like we are at the stage that like an assembly language in 70s or 80s. So assembly language of quantum computing is like that. We give this to our compiler. This is a Cisco compiler. You can give as a customer or user your network topology and how your quantum computer are connected together and what is the network, and the rest is done by the software. It schedule your network, schedule your compute, and execute your program on top of that. So it's a combination of the network controller, and so in fact I have a demo of that which I show you shortly. What we are building, we are now in the process of how to make it available to wider community, or we have built, not we are building, we have built. What we call it is the Quantum Network Development Kit. That's a simulation, emulation, and control of real hardware. What does it mean? That there is a software cloud base, you can access it. You can first of all connect to our switch, source, and everything we have in the lab, detectors, and build your own network using the resources that we have to play with it, to test your idea. You can also scale it using simulation. So you can scale, you build a larger network and simulate it, and also to see how does it work. In terms of this support both network and computing technology. In terms of computing technology, you can bring your own computing model or characteristic. In terms of the network, is particularly focused on the Cisco networking technology, quantum networking technology, and it can basically give you a very good tool to try your design idea for quantum network, or if you want to see what does it take if you want to upgrade your network infrastructure to quantum, to support quantum network, what you have to do, especially for upscaling or training of your people. So this is a picture of the GUI. I hope I get the time to go through that picture, the GUI of this. But before I enter the demo, I have a couple of more slides. Oh, that's something important here. I want to mention that our simulator is not only simulator and control. We are releasing gradually, as of end of this month, a series of APIs. So you can start accessing this and, for example, run your own algorithm on top of that for control and management, if you like, or optimization algorithm on top of that, or even execute your quantum computing on top of that yourself. So that's also, we are releasing that. Now, some advertise what we do. We just recently opened our lab in Santa Monica, LA. So we have a whole quantum technology lab there, and is opened. You can see the picture of opening by senior leadership of the Cisco. And really, if I want to summarize it toward the end, what is our goal in Cisco? We want to build a quantum network that really make a quantum computing a reality 5 to 10 years sooner than what is expected now. We have a relatively large team. These are the scientific leadership of the team, but we have a support of the OutChief, which is the incubation group of Cisco engineering team, our optics, our security, and a lot of universities we fund or we work or collaborate. We are not only engineering group, we publish a lot of scientific contribution to the community. You can search the Cisco under any famous journal that publish about the quantum. You see a lot of publication from us and a lot of patents. So final slide before the demo. If I want to say you really leave with 4 key takeaways out of this session, is first of all, quantum networking, I hope I managed to give this message or convince you is completely different from the classical network. You cannot just upgrade your classical network to build a quantum network. You need a completely ground-up approach. Through the scale-up, really, we can make a quantum computing something useful. It's not just become a scientific exercise, become a really practical application, and we make it really useful, accelerate the availability of 5 to 10 years. Quantum networking is not only useful if you have a quantum computer. It has a many practical applications. I gave an example of 4 of them today in the classical world today, so people can use it with today to solve their own the problem that they have now. And finally, that I hope you have seen that we are really building a practical and scalable quantum network. So what I am going to do, I plan to do 2 demos. Or 3 demos now. I think I have time for 2 demos. 1 demo is recorded because I want to be safe about our compiler. 1 demo, I am going to use our QNDK, connect remotely to real hardware, our source and everything in the lab, and see, you see that. Let's figure out the second one works, but the first one, I am sure the video is going to work. So let's go to the first one.
Hi, my name is Sam.
And I'm Adam.
And today we're going to talk about the Quantum Network Development Kit, or QNDK. So to start off, here's an analogy. Let's imagine that you want to make a stir fry for a dinner party, and you only have small frying pans and cutting boards to prepare the ingredients. You need to account for the fact that some ingredients need to be prepared together, while others can be prepared independently and then merged in later. How do you effectively use your limited resources to complete this workload? QRDK is a tool set to help you do this, to break down big quantum programs into smaller executable chunks that work on today's state-of-the-art chips. For context, meaningful quantum work will take millions of qubits, but the current state-of-the-art chips only support hundreds of qubits right now. So instead of waiting to vertically scale these quantum processing units, these QPUs, let's horizontally scale, let's network them together and break up your quantum programs to run distributedly in this environment. So in our quantum development kit, quantum network development kit, it will take as input your quantum circuit, also known as your quantum program, and a description of your network topology, what available resources you have. And it will compile it into chunks that will be executable in your on your actual resources. There's a scheduling component and a simulation component. But at the end of the day, the output of this is the instruction set that you want to execute across your available resources. So this is an ongoing project. We're actively continuing to improve it. And Adam is going to take it away with a little demo now.
Thanks. Here's a demonstration of our quantum network development kit as a deployable, containerized, API-driven service to be used by researchers and network engineers alike in their quantum data center. I will show examples for loading quantum network topologies and storing device information in our graph database, along with being able to run this locally and visualizing your results. Here's an example of running our graph partitioning algorithms against user-defined quantum network topologies. Here you can see the loaded Cisco data center topology with corresponding Cisco devices and quantum processing units, along with the corresponding qubit assignments. Once ran against our novel algorithms, you can see the quantum processing unit EPR pairs and the corresponding qubits that have been allocated. In addition, we have, for our network engineers, a suite of APIs where we can load network topologies, run compiler and scheduler algorithms, and host the resulting outputs in our graph database that can be used downstream in the controller and other tasks. Thanks again.
Okay, so in a danger of going a couple of minutes over time, I try to show you what we, real hardware connecting the lab. Let's finger cross works. If it doesn't work, okay. So this is our GUI canvas for the working with real hardware for controller. I try to, oh yes. So if I go here, I load, I mean, that's you can do simulation here. I don't go through that. If you are interested later on, we can see, or you can look at the recorded presentation, other sessions. So I run a real, this is a real hardware. So this is a real lab. So what's happening here, we have our entanglement source. It's a very simple demo. Entanglement source here, that's a laser pumping the source. And then what comes the idler or two entangled boxes or photon. One comes from one output port, the other output port goes to that. So one output port goes directly to detector, where we detect. The other pair of the photons or a box goes through a switch. And then we switch it, and now we switch back. And what you see, the result here is going through a very short fiber to detector again. So essentially back to back. Now you see that at this stage we have around 1.2 million pair of entangled photon per second generating with this setup, and the fidelity is around above 90%. So now what I want to do, I switch this line to go through the 100 kilometer of fiber spool. So you will see that degradation. So that's to show that really effect of the distance on entanglement. So let me, okay. Oh, yes. So you see now at a large number of spools, that large length of fiber, large length of fiber, we reduce entanglement quite significantly. And then the rate dropped, and then the fidelity also dropped, the efficiency of that. So it means that so what does it mean exactly, this figure? This short distance, one of the boxes arrive healthy, some of the boxes, they don't arrive here. From the other side of the arm. So from two entangled box. You have a pair of the box, one arrives, the other doesn't arrive. So with that, I will conclude my presentation. If you would like to see really, you would, first of all, don't forget your session evaluation. And the second thing that I need to tell you, let's tell everything. You can continue your education. That's important. In Cisco also, if you go to Cisco Research, there is a whole bunch of video, blog, and papers very simply written about the quantum. You can see them. That's another thing that I want to mention. And with that, thank you. Thank you very much.